Okay, greetings everyone. This is lecture 3 of EEE 23, and the topic is on electric flux, Gauss Law, and the Divergence theorem. Okay, to start with the discussion, let's have let's see the experiment of Michael Faraday. An experiment he conducted in 1837, where you have two concentric spheres with the inner sphere right here charged by positive q. Okay, this charge attracts the negative charges and repels the positive charges in the outer sphere. Okay, so now note that both of these spheres are hollow, and between them is an insulating material. Therefore, no charges can travel between them. Okay, so the negative charges are attracted to the positive charge, and the positive charges are repelled by the positive charge. Okay, so the result is this sphere outside. So given that your inner sphere is charged with positive Q, the sphere outside is electrically neutral, mainly because there is no pathway for the positive charges to flow along. Okay, so as you know, recall that your positive charges attract negative charges and repels positive charges. Now, what happened is that when Michael Faraday grounded the uh, outer sphere, so that means that the positive charges flowed to ground. Okay. So take note that this is momentarily, okay, momentarily connected the outer sphere to ground. So when measured, the outer sphere has a total charge of negative q. Okay. So and when Faraday carefully dismantled the setup, the charge inside was not changed, which is what was predicted because this is an insulating material. Therefore, no charges should flow out of the positive charge. But the main thing here is that the charge magnitude of the inner sphere is equal to the charge magnitude to that of the outer sphere. Okay, so regardless of how much charge Faraday put in the inner sphere, the outer sphere would follow suit with the same amount of charge but with different sign. Okay. So mainly, the magnitude of the charges is directly proportional to the amount of charge inside. Let me restate that. The magnitude of the charge of the outer sphere is directly proportional to the magnitude of the charges inside the sphere. They are we're actually equal in magnitude. Okay, so regardless of how much charge Faraday put in, your outer sphere will follow suit. So there's something actually that has caused the charge to be induced to your outer sphere or outer conductor. Faraday called this displacement flux or electric flux phi. Okay? And by experiment, that phi is equal to the charge that was initially put in by Faraday in the inner sphere. Okay? So the electric flux then is the measure of the amount of electric field passing through a surface. As we all know, the electric field applies a force to your charges, and this is actually the what displaced the positive charges from your outer conductor. Okay, so the electric field from the inner conductor displaced the positive charges in the outer conductor. So the electric flux, then the amount of displacement, is quantified as psi, and it's equal to the charge inside the inner conductor. And that is the amount of flux passing through your outer conductor. Okay? So quantitatively, that flux is equal to Q. So it's directly proportional to the amount of charge causing the flux. If you use SI units, the constant of proportionality is 1. Now, if we look at the electric flux density of the inner sphere and the outer sphere, so first let's define it. Electric flux density is the amount of flux per unit area. So it has a unit of coulomb per meter squared, or basically charge per unit area, or well, actually the right way is electric flux per unit area. So this is a vector field from the flux density class of vector fields. It's different from your uh, electric field. So electric field is also a vector field, but this is actually a force density. Sorry, kind of a force density for your it's a force density class of vector fields. Okay, while your D is actually a flux density. The direction of D is at the direction of the flux lines that at that point. Okay, and the magnitude is equal to the number of flux lines crossing the surface, okay, normal to the line. So by definition, if you have a surface, okay, the area vector for that surface is the direction of your flux density. All right. So note that D is a vector. So for example, consider Faraday's experiment. You have an inner sphere of radius A and an outer sphere of radius B. Electric field emanates from radius A, from your inner sphere to the outer sphere. Okay, so we want to determine the flux density. So just some remarks. Charge inside the inner sphere induces the charge outside or on the outer sphere. Okay, the direction of electric flux is along AR hat. Why? Because of the symmetry of the problem. Okay, so if you look at the flux lines between A and B, the flux lines are perpendicular to the surface. In this case, the surface is a sphere. Therefore, the normal vector that is perpendicular to the inner sphere is actually AR hat. So now, the surface area of the sphere is 4 pi r squared. So if you want to get the unit electric flux with the unit area, sorry, let me rephrase that. If you want to get the electric flux per unit area, we will just divide the total flux, which is equal to the charge, okay, divided by the total surface area of your surface. And that is this expression right here. So this is true for any sphere between A and B. Okay. So if we shrunk the inner sphere to a very small radius, so it means it's now a point charge. Then the electric flux density is equal to this, and A would just be 0. So actually uh, it's actually uh, true at this range, right? So recall that the electric field due to a point charge is equal to this, and it so has it that when you want to relate D and E in free space, this equation uh, shows up. All right. So D is equal to epsilon sub 0 times your electric field. Okay. Now what if we have a continuous source of charge? So the flux density at the point P due to a continuous charge distribution can be expressed as just the summation of your individual charges, okay, the flux due to individual point charges to your point P. So your summation of your individual point charges, they have their own density, okay, times their small volume. Okay, that's the charge. That's the total charge on this point. And just use the formula, right here. So this formula came from this right here. Okay, this is AR hat. This is your distance squared. So epsilon naught is not present. So this is for your when you take the limit of your delta V as approaching 0, you'll end up with an integral. Okay, so you'll end up with an integral function. All right. So now we have you can generalize this Faraday's experiment. So Faraday's experiment can be generalized to any closed surface, and the total flux passing through this closed surface is equal to the total charge enclosed by that surface. So in terms of very small areas within that closed surface, by convention, the unit vector of your very small surface for a closed surface is always going outside of the surface. Okay, so now the total flux, or sorry, not the total flux, the differential flux or the very small flux that is passing through this very small surface is equal to the the electric flux density dotted to the surface area vector or differential surface area vector. Why is it a dot product? Because we're forcing the flux to be, no, not really forcing. The flux should be parallel to the surface area vector, or the flux should be moving normal to the surface. And the vector that is normal to the surface is equal to the vector of the surface area. That's why this is a dot product. So if we integrate that, so we integrate that to every point on the surface, right here. We integrate that to every point on the surface. And that is equal to your charge enclosed, which is equal to the total flux, which is equal to this closed surface integral of this expression. Okay? So now let's try to apply Gauss law. Consider then a point charge positive q located at the origin, causing an electric field in free space. So you already know that. Now we have your electric flux density, which is this. Where did we get that? Sorry, where did we get that? B is equal to epsilon naught times E. So if we enclose the point charge by a spherical Gaussian surface of radius A, the flux density on all points on the surface is equal to this. We just evaluate the flux density at the radius equal to A. Okay. So why is it spherical? Why did we choose a spherical surface? Mainly because of symmetry. Okay. A spherical surface has a unit vector all over. So let's visualize. The unit vector at any point on the surface of that sphere is air hat, which matches this equation right here. Has a direction air hat. This is visualized in this slide. So your sphere of radius A at this point, the direction of the unit vector at this point for the differential surface is from your origin to this point here on the sphere. The unit vector is just a magnitude of 1 here in this direction there. Okay? So now we can get the differential surface area for a sphere. It's equal to this. So where did that come from? Well, you have a very let's look at a very small patch in the surface. Recall that this is equal to an arc length. So this is an arc length, okay? Differential arc length. Differential arc length equal to A times sine theta. Where did that come from? Well, That is the radius of this arc right there, a sine theta. So this the radius here. Where did that come from? Well, we know that the radius here is a. The radius is a. The length of this is equal to a times sine theta because theta is the angle here. So you kind of form a triangle like this. A, and this is what you want, some radius rho, and the angle here is theta. Therefore, the radius here, rho, is equal to a sine theta. So this is the differential arc length times the differential angle here. So where did this come from? Okay, so d phi is the differential angle here. Okay, from here to here. All right. So this is a sine phi, so a sine theta d phi. This one is also an arc length. So let me delete all that. This one is also an arc length right here that is defined by this arc here. Both this both these lengths are of radius a, and it has a differential angle d theta. Therefore, this is a d theta. So this is your differential arc length, and you multiply it with this differential arc length here, which is a sine theta d phi. You'll get your differential area on the AR hat direction. Okay? Recall that a surface area is equal to your distance vector crossed to your distance vector. In this case, a differential surface is equal to dl cross dl. Anyway, this is the final form of that. So cross AR hat. Therefore, the integrand is your uh, the expression for your flux density dotted to your differential surface, which is equal to this. Okay, so this is a dot product. You just need to delete this. Okay, so the dot product, the output is a scalar quantity. So now you you integrate it over the closed surface, which is a sphere, and the bounds of that is dependent on theta and phi. If it's a complete sphere, then the bounds of theta is from 0 to pi, and phi is from 0 to 2 pi. Given these bounds, you can separate the integral into two parts. You can integrate it separately with d phi, integrate it separately with d theta. So you separate uh, all the terms with the same variables in the same integral. So you integrate sine theta d theta, and you integrate d phi by itself, and you'll get this expression right here. Okay. Now, if you evaluate these two with their bounds, you'll get this negative cosine theta will be equal to 2, 1 minus negative 1. And this is 2 pi minus 0, which is 2 pi. And if you multiply that, you'll just get this here. So the total flux is equal to the total charge enclosed by that surface, which kind of is the definition of Gauss' law. So, some remarks on Gauss' law. Well, actually, if you don't know the expression for ds, you can use Gauss' law to solve for it. Knowing that you have enclosed a charge on your Gaussian surface, so you have to define ds, and with ds you enclose a charge, you can solve for d. Okay? So, the evaluation of the integral is easy if your closed surface, the one you chose or the one you designed, satisfies these conditions. ds, or your flux density, is either normal or tangential to the closed surface, so that there are terms in this dot product that either becomes maximum or zero. Okay? So there's no angle between them. So that makes integrating easier, right? So this part is the normal component of the flux density with respect to your surface. or 0 if it's tangential. So you have to choose a surface that fits this description. And on that portion of the closed surface for which it's not 0, then ds is constant. It does not vary at any point in that surface. Okay, so to visualize that, let's have an example. So for a point charge, we chose a radially outward, sorry, let me, let's choose a radially outward Gaussian surface. And the radially outward Gaussian surface at any point is actually a sphere. So at any point on the surface, the field is actually normal, okay, due to the electric field of your point charge. So with that, the electric field has a constant magnitude at any point on the surface of the sphere. Okay? So we can solve for the electric flux density for this Gaussian sphere of radius r, or Gaussian surface, which is a sphere of radius r. Then if we invoke Gauss law, we have the enclosed charge, which is equal to this, which is q, so it's a point charge, equal to the closed surface integral of the ds at any point on the sphere, dotted to your ds, which is your differential surface area. So it's right here. Since ds is constant, you can factor that out of the integral. You can move that out of the integral, and you'll be left with this. Okay? So ds is constant. You just integrate it with integrate the surface. So the surface is a sphere. Therefore, the bounds is from 0 to pi. Your d theta is from 0 to pi. And d phi is from 0 to 2 pi. So you integrate that. You'll get this expression right here. That is equal to the total charge enclosed divided by 4 pi r squared. You'll get this expression right here. So this is the uh, electric flux density of a point charge with charge equal to q sub enclosed. Okay? So now let's look at the flux density due to a uniform line charge. Okay? So due to symmetry, the electric field is always radially outward. So we expect the electric field to always be radially outward. Okay? Something like this. So to the Gaussian surface that fits that description is actually a cylinder. A cylindrical axis, which is your flux density, is always normal. Okay? Your flux density is always normal, 0. And that is because your differential surface here is also in the direction of arrow hat. Or, not or, and a part of that closed surface is along AZ hat, which is normal to your electric field. Okay? It's normal to your electric field right here. So your d rho is constant all throughout this point on the cylinder, these points on the cylinder. But on these points, you don't have any electric flux because the direction here is normal to the electric field. Okay, so you limit this then to a cylinder of height L. So your Z is from 0 to L. Okay. Okay, so now to evaluate that. Invoking Gauss law, the charge enclosed is equal to the closed surface integral of your flux density dotted to your flux density dotted to the differential surface. The differential surface has three parts: the top, the bottom, and the sides. Alright? So evaluating that, knowing that ds is constant all throughout this uh, Gaussian surface, we get the integral of ds on the sides plus 0 times the integral of ds on the top. Why is it 0? Because the dot product of your field here is 0. Okay? And the integral of the bottom also the same, since this is also a normal component. So you'll be left with just the expression for the sides. And what is the bounds of this given surface here? Since you're going one whole revolution on the phi axis, your phi is bounded from 0 to 2 pi. And since your z is bounded from the origin to L, your z is bounded from 0 to L. And you evaluate this integral, and you get 2 pi rho L times ds. And solving for ds, we get the ds equal to this equation right here. With your Q enclosed, the enclosed charge of your surface, that is equal to the line charge density times the length L. So that's the total charge enclosed by the surface right here. Okay? And you'll get this expression right here for your electric flux density. And it's actually, if we invoke the formula, ds is equal to epsilon naught E. Okay? We can solve for the electric field along every point due to the line charge. And you'll see that the electric field expression from here is actually equal to the electric field expression from the previous lecture for a uniform line charge. Okay? Now let's look at the electric flux density due to a coaxial cable. What is a coaxial cable? Coaxial cable is basically a cable with an inner conductor and an outer conducting shield. Okay, the inner conductor is solid and the outer conductor is hollow, and basically your inner conductor and outer conductor is separated by an insulator in between them. For now, let's assume it's free space. Okay. Oops. Oh, there you go. Okay. So coaxial cable has an inner conductor equal of rho of radius A, outer conductor of radius B, and the charge density is on it's just on the outer surface of your inner conductor. Okay? So the charge density is only on the outer surface. There's no charge inside the inner conductor. Okay? So it's all on the surface of the inner conductor. So what is the electric flux in between them? So we choose a Gaussian surface that is also cylindrical. So some Gaussian surface of length L due to symmetry again. So if you apply Gauss law, we'll get this expression right here. And again, ds is constant. Excuse me. ds is constant along the sides of the chosen Gaussian surface again. So there's no field here and no field here. Okay, so there's nothing. All right. So evaluating that, we get 2 pi rho L times ds, which ds is your electric flux density magnitude, which is equal to 2 pi A L times rho s. This is the total charge enclosed by this surface. Where did this come from? It's equal to the surface charge density on the inner conductor. Okay? Surface charge density on the inner conductor. And that's rho s. And multiplied by the area from 0 to L of this inner conductor right here. That's equal to this 2 pi A times L. So you can now solve for ds. ds is equal to this expression right here. So some comments at rho less than A, flux density is 0 because if we reduce the Gaussian surface to inside this conductor right here, oops, sorry. Anyway, you can imagine that. Okay. So if we have a Gaussian surface within the inner conductor, there will be no charges enclosed because the charge density is only located at the outer part of the inner conductor. Okay. At rho greater than B, we need to assign a charge density on B such that anything outside B, okay, if we take a Gaussian surface outside, so greater than B, something like this, okay, let me clean that. So some Gaussian surface that is something like this, okay, much bigger than B, something like that. So you can imagine it, I hope. So if we choose a Gaussian surface that is greater than B, there shouldn't be any electric field that is leaking out. So that's actually the purpose of the shielding outside the coaxial cable. We don't want any electric field leaking out of your coaxial cable, and because that might cause interference in the outside world. Okay, so that's the effect of shielding. With that, it must have a charge density that is equal in magnitude. Sorry, not the charge density. It must have a total charge that is equal in magnitude but opposite in sign as that of your inner conductor. Now, where do we hear that? Or where did we see that? That's actually going far back. That's actually Faraday's experiment. Okay? Your inner conductor and your outer conductor must have the same magnitude of charge and different signs. Okay? So most of the time, this part of your coaxial cable, the outer conductor, is grounded. If it's grounded, then the charge inside repels the charges outside and leaves a charge on the outer conductor that is equal in magnitude but opposite in sign. Okay, and how do we get that? We need to have a charge density on your outer conductor, which has a radius b, that satisfies this condition. Okay? So how do we do that? We get the total flux. Sorry. Let me. There you go. We get the total flux on this outer conductor right here. Okay. So imagine a Gaussian surface with the same dimensions as your outer conductor, but we limit it to a length L. Okay. Then we get the electric flux density on this surface. So basically just evaluate this with respect to rho is equal to b because that is your the radius of your imaginary Gaussian surface. So that is rho s a over b. And that is now the charge density of your outer conductor, but it should have an opposite sign. Okay? So this results into a flux density outside your coaxial cable equal to 0. Why is that? It's because if we assign a Gaussian surface outside or greater than the length or the radius of the outer conductor, the charge enclosed by this Gaussian surface is 0. Therefore, if it's 0, there's no flux that is coming out of your coaxial cable. Okay, so that's the importance of the outer conductor actually when transmitting information over a coaxial cable. So what is the information actually normally transferred in a coaxial cable? The normal coaxial cables that we see is actually on our TVs. Now we're evolving to a black box type TV that doesn't need a coaxial cable at all. No, wait, it actually needs a coaxial cable to connect to the antenna. Right? So that information is being transferred over a coaxial cable. And the shielding is there to prevent any leakage of electric field from your coaxial cable. because that leakage actually is also a loss of information. Anyway, so let's move on. Next part is how about the electric flux density due to a sheet of charge with charge density rho sub s. So we assign a Gaussian surface that looks like this. In this case, the electric field is normal to the top instead of the sides. So the electric field here, there's no electric field component here, therefore the flux density is equal to 0 in this direction. Therefore, the flux density is actually going out here and here. Right? So the total charge enclosed by the surface is equal to this. So the charge here is equal to the density multiplied by the area, which is equal to actually it's not relevant. Let's just call it S. All right. So the total charge enclosed is equal to rho s times S, which is equal to 2 times D. D is the electric flux density times S, which is the total surface area of this part of the surface. Why is it 2 times S? It's because it's recall that it's D dotted to S or ds. In this case, the let me clean that. There you go. So in this case, there's actually an electric field that is in this direction, and the surface area vector in the bottom part is going towards the same direction. Therefore, if we take the dot product of that, it will be positive. Same is true with this. Also positive. So if we add those two parts right here, the total flux is 2 times d times the surface area here and here. So that's 2ds. So we can solve for d here. That's equal to the charge density divided by 2. And the electric field is actually equal to d over epsilon naught, and it's equal to this. And this is actually the electric field that we solved in lecture 2, in the previous lecture. Okay? Alright. Okay, so this is just for your coaxial cable. I did not haven't edited that part. Anyway, okay. So part 1 of the lecture ends there. The next part of the lecture is dealing with the asymmetric charge distribution. How do we solve for the the electric flux density if we have an asymmetric charge distribution? How do we uh, put a Gaussian surface there? Okay. So see you on the next lecture.